Hello, everybody. I think it's 12 now in Central European time. So time to start the webinar. I don't know if we want to wait a little bit more, a couple minutes. In the meantime, I'll do a short introduction. My name is Esteban Bernechea. I'm a principal consultant for ORS Consulting, which is a technical safety consultancy group formed in Scandinavia mostly, but now with new locations recently in the UK and now in Turkey as well. So going strong and with great technical capacity to help with any process safety, technical safety concerns you may have. My background is in chemical engineering, and yeah, I do mostly. I'm a certified functional safety engineer. I work mostly doing process hazard analysis and helping clients go through the functional safety life cycle defined in ISD 61508 and ISD 61511, depending on which industry they operate in. And yeah, that's mostly what I do, help organizations through the functional safety life cycle. As you may know, the first stage of that is to perform a hazard and risk assessment, right? Where you identify the hazards that your process may encounter. And after that, you have to allocate protection layers to protect against those hazardous events. And then you have to decide more or less how good those protection layers need to be, if they are electric, electronic, programmable, electronic. And that's what we call SIL determination, right? So that's how do we determine what safety integrity level each of our safety instrumented functions should have. Now, most of you, if you work with functional safety, you will be very aware of what the normal process to do this. You may know RiskGraph and you may know LOPA, which is the main tool that we use, or the main technique that we use for SIL determination. But I'm here to talk today about a different technique that's not normally used because it's more time consuming, a little bit more complex, but it's also very useful for doing SIL determination. So I'm here to talk about fault tree analysis and how to use it for SIL determination, when to use it for SIL determination, and if we are going to do that, why do we want to do that, and how do we do it, right? So I think, yeah, we are who we are. Hopefully more people will join, but let's get this running, right? So using fault tree analysis for SIL determination, the main objective of this webinar is for us to provide an overview of how risk reduction is done to determine the safety integrity level of safety instrumented functions in general, right? To explain what the risk reduction model for a hazardous event is and what we are trying to do there to determine SIL, to determine that this would be the basic approach, and then to understand how you can use fault tree analysis to do that and in which cases you want to do that. We don't aim to provide in this webinar an in-depth explanation of the fault tree analysis technique. So we are not here to discuss a lot about Boolean logic, how to perform the calculation in the fault tree, how minimal cut sets are defined, etc. Right? So this is not focused on fault tree analysis, but on how to use FTA to get to determine the SIL of safety instrumented functions. Okay. Of course, I think I forgot to say there is a Q&A here in the chat in the Teams meeting. If you have any questions at any point, just put them there. At the end of the session, we will go through all the ones we can, right? So let's get to the meat of it. Now, you know, I always like to start these conversations talking about what safety is, what risk is, and what we are trying to do when we look at each of these hazardous scenarios. So I like most, the definition of safety I like the most is the one presented in IC 61508, which says that safety is defined as freedom from unacceptable risk, right? And that, to me, it's a great concept because it gives you there, in a nutshell, the foundational blocks for everything we do in functional safety. So it tells you that there is, there is a risk and there is a level of acceptable risk. So if risk is zero, well, then there's no need for any of this, right? So safety is freedom from unacceptable risk. So freedom is us, safety is us achieving that acceptable risk, which means in the activities we work in, there will always be risk, and there is an acceptable level for that risk to exist, right? Now, risk is defined by the probability that something goes wrong in a specific period of time, right? Causing specific consequences. So this probability in a specific amount of time is what we normally refer to as frequency, right? So the probability of something happening in a fixed framework, in a fixed time frame. So for example, once every year, once every 10 years, and leading to a specific consequence. So those consequences can be consequences on the safety of people, consequences on the environment. So it could be fatalities, it could be multiple injuries, it could be a significant environmental impact, but it could also be related to assets, right? So risk is the measure of the damage caused on people, the environment, or material property in terms of frequency of occurrence and consequences of the event. And we know we can sort of express this mathematically just as frequency times consequence, right? Now, when we build a risk reduction model for a specific hazardous event, we have the risk of a specific consequence, right? And that is fixed. The consequence is fixed. So this line is representing risk where a consequence is fixed. This is, for example, a single fatality for a specific hazardous event, right? So this may be overpressure in a specific vessel. This may be a pump running with blocked outlet. This may be, a shear pipeline rupture, if you want, any hazardous event that you have identified during a process hazard analysis or a similar review. But you cannot conflate several scenarios into only one. So one hazardous consequence, and it may have different initiating events leading to it, but it has to be one specific consequence, one hazardous event that you're looking at, right? And when we know that consequence, we can define an acceptable risk. So that will be, depending on your organization and depending on the regulatory framework in which you are operating based on your geography, that could be, maybe once every 10,000 years, it's acceptable to have a single fatality, or once every 100,000 years. Or if you're talking about assets, it could be that the organization is willing to lose a specific amount of time. Not willing, but it is considered acceptable to lose a specific amount of money in, once every 1,000 years. So that's the frequency that you, as an organization, or maybe the regulatory body where you operate, will tell you, right? This is the acceptable risk for that consequence, for a similar consequence to that. So we know our acceptable risk for a specific hazardous event with a clear and unique consequence. As I said, in this model that we're going to follow, and when you do, SIL determination for safety instrumented functions, which are mostly preventative safeguards, the consequence is normally fixed, but we decrease the frequency of the event until we reach an acceptable risk. Now, the acceptable risk, the first thing we need to define is how many times per year we could cause, or how many times per unit of time that event could occur within our process, within our system, right? The gap between the unmitigated risk frequency and the acceptable risk frequency we refer to as the risk gap, right? So bridging this gap between what happens without any safeguards and what is acceptable is the goal of all the preventative protection layers in the process industry, right? When we install alarms, when we install safety instrumented functions, and then we put PSVs, that's what we're trying to do. We're trying to reduce the frequency of the hazardous event down to an acceptable risk level. Because by introducing preventative layers, we reduce the frequency of occurrence of the ultimate consequence, right? The lower the probability of failure of these protection layers, the bigger the space in the risk gap that they cover, right? So the lower the probability of failure on demand of each protection layer, the more we are bridging that risk gap. Now, not all the risk reduction is achieved by means of preventative protection layers. We also consider condition modifiers in these models, right? So you don't have to cover all the risk gap with preventative protection layers if you can. You can also consider that maybe people are not present in the facility all the time. You can consider that the ultimate consequence will only occur if you have ignition of whatever was released, and that may not happen every time, right? So you basically can define what the risk that you assign to condition modifiers is, right? And then you know more or less what is the gap that you need to cover with protection layers. Then you have to define also which of these protection layers are electric, electronic, program, electronic, or have electric, electronic, program, electronic components, and which ones don't. The ones that don't are out of the scope of IC 61511 and IC 61508, right? So we will assign a risk reduction to them, but more based on industry standards and RID, our rules of thumb or data from the process industry. While for the ones that are EEPE devices or that have EEP components, we need to perform SIL determination, right, to see what their safety integrity level is. So this space in the risk gap, which is covered by the safety instrumented function, is equivalent to the safety integrity level of that function. That's what we are trying to find when we do SIL determination, this space in the gap, right? So determining this space in the risk gap is what we do when we do RiskGraph or we do LOPA or we do fault tree analysis for SIL determination, right? This is what we want to find. And if you have sort of an unidimensional a scenario where a simple scenario where you have, maybe a few initiating events, but it's all very clear as to how the system is protected and what the source of the hazard is and how to eliminate that or how to prevent that hazard from manifesting itself. Then you can do that easily with a LOPA, for example, and you can do that easily with a RiskGraph. And then you don't need to do fault tree analysis, right? So, for example, if you're using LOPA, these techniques will allow you to, or if you're using RiskGraph, it's more or less, we're always doing the same thing mathematically, more or less. RiskGraph is qualitative, but if it's properly calibrated, what sits behind the RiskGraph is something like this equation. So what we're trying to do is to multiply the probability of failure on demand of all the independent protection layers by the probability of occurrence of the condition modifiers, by the frequency of the initiating event, and then add that for all the initiating events. And if we divide the target frequency by this mitigated event frequency that we're calculating, we will get the SIL for our safety instrumented functions, right? We will get a number that sits somewhere in this band, hopefully, and hopefully below the 3, because if you're in the 3, that's not good. And if you're over the 3, that's normally considered a requirement to redesign your system, right? Or maybe to do a more quantitative assessment. So when we're trying to do any of these techniques, these are the numbers that we're trying to get to see how good our safety instrumented functions need to be in order to get to an acceptable risk level, right? Now, we normally do this with these different techniques, right? There is a variety of techniques to do SIL determination, and they are in a spectrum of being more quantitative to more qualitative, right? Completely qualitative is the RiskGraph, although as I said, if you do calibrate it properly, there is a quantitative aspect to it in the calibration process. Then you have semi-quantitative methodologies, which are LOPA and risk matrix, where they are sort of order of magnitude type of methodologies in which you do a lot of assumptions. And so that's why we say they are semi-quantitative. You don't go into full detail of the scenarios, and we normally apply them for, 95 to 99% of the scenarios can be done with a LOPA. And then you can go fully quantitative with a fault tree analysis. Now, fault tree analysis goes more in depth with the detail of the scenario, and it's gonna take more time to resolve. So it's gonna take more money as well to do it. But sometimes you cannot find the required SIL using LOPA or RiskGraph. Even like that would be even more difficult for a complicated scenario. So you can mostly, as I said, you can mostly use LOPA for every preventative safety instrumented function out there, 99% of them. But sometimes there is a requirement to do something more because LOPA just doesn't have the required dimensions for you to solve the problem. So this happens when you have very complex scenarios where there are more than one SIF interacting and different sources of the same hazard. So one example I encountered recently, a month ago or so, was that we have several sources of pressure which converge into one processing system, right? So imagine you have multiple oil wells all going through a lot of manifolds and ending in a common separator, right? And that's a fairly typical arrangement in oil and gas, right? So the different pressure sources, so the different wells, may have different design pressures. They may have different maximum wellhead shut-in pressure. They may coming from different formations. So that would be the most complex problem for this. And the common processing system is normally not designed for that pressure, right? So it's normally not designed for the maximum pressure that the sources can generate. So, however, the common system has initiating events which result in overpressure from any of these multiple sources, right? So if I block that common system, I get overpressure from all of the wells at the same time. Each of the pressure sources, each of the wells is provided with protection layers to prevent overpressure, right? So each of the wells may have a high pressure trip, and they may have PSVs. In the case I saw, they had PSVs, but this is sometimes not that common to have a PSV just coming out of the well. So the common system is protected by each of the pressure sources, not by itself. So there are parts of the common processing system where you put all the wells together and you go in a flow line. After a manifold, that flow line is designed for a lower pressure than the maximum that these wells can produce, but there is no high pressure trip or anything to protect that common line. You sense high pressure in each of the wells and you close each of the wells, right? So at some point you have to calculate the probability of any of these failing when you have a common closure in the system. So how do you know that the risk of overpressure for the whole system is acceptable? You cannot do the LOPA of each one of these functions because then you are missing the interactions between them because they are sharing common initiating events that will put a demand in all of them at the same time. And if one of them fails, you will get overpressure of the system. So you sort of need to do the LOPA of all these functions at the same time if you were to do it with LOPA. And that I don't know how you would do it. I guess you can, make like a custom worksheet work for you, but it's not the way to go. That's gonna be way too difficult. So how to model a system like this with different safety instrumented functions protecting against common and specific scenarios during a LOPA? I don't. I think I could think of a very complex way of doing it with a worksheet with a LOPA methodology, but it would take more time than doing the full tree, I believe, and it would get probably a worse result. Another example that you may have encountered or that you may be thinking of is backflows from different downstream points coming back into a single equipment that is designed for lower pressure, right? So, for example, you have a chemical injection system that is injecting to different points of a process, and each of these different points may have different operating pressures. And then if the chemical injection system fails, you may get backflow from any of them, and each of them is protected with a different backflow protection layer with a backflow safety instrumented function. So how do you know whether the risk of overpressure in the common point is acceptable when you have to look at different SIFs at the same time? You again need to model different SIFs which are protecting against common and specific scenarios for different pressure or temperature sources with different IPLs. So each one of these sources may have different IPLs, and you need to put all these in one model. So how do you do that? You do that with fault tree. So I tried to explain this graphically, right? In the previous one, we had one line. Now we have maybe 3 or 4 different lines which are protected by different safety instrumented functions. So at that time, LOPA becomes a little bit too one-dimensional to be used for this process, for this problem. So when you find something like this, normally LOPA is not going to give you a full answer, and it's not going to give you a really detailed answer. So for cases like those, you need to do fault tree analysis, right? So again, most of the time you don't need to use fault tree analysis. Most of the time you can use LOPA or RiskGraph or whatever else you may need, but not fault tree analysis, because for simple scenarios it will take you too long to just develop fault trees for each scenario. It's going to be much faster with LOPA or with RiskGraph, whatever you choose. But when you have a system that is very complex, have different initiating events in different parts of the process, protected by different IPLs at the same time or different SIFs at the same time, but producing the consequences in a common part of the process. When there are interactions between SIFs, IPLs, and initiating events which are not straightforward to model in a line-by-line model, such as the one provided by LOPA, and when you need to account for common cause failure between the different IPLs, between the different safety instrumented functions. So basically, when 2 different SIFs in parallel are protecting one common point. So what happens if any of the 2 fails, or if both of them fail at the same time? Can there be a systematic failure between these 2 or 3 or more than that SIFs, which could cause them all to fail at the same time? So when you have to consider that, and when you want to add that level of complexity in the problem, then you have to go for a fault tree analysis. Maybe you could go for something else, but fault tree is the way to go for me. So just to go quickly through it, fault tree analysis is a deductive methodology in which you apply Boolean logic to determine the combination of basic and intermediate events that lead to a top event, right? You're familiar with fault trees, you know that. So you know that you normally have different gates, different types of gates. The first one is the top event, which describes the conditions that occur due to a combination of basic events. So for us, for example, this would be our hazardous event. This would be an overpressure at a specific part of a plant. And then this event happens because of the combination of different other events in different sequences, right? So to create those sequences, we go from basic events, which require no further development, and you know the frequency of occurrence of them, right? So you can quantify how many times per year they happen, and you sort of develop them based on Boolean logic, or and gates to get to the top event. So or gates are the ones that you do when the next higher event occurs if any of the inputs is occurring, and gates will lead you to the next event forward or upper if all the inputs occur at the same time. So of course you can start thinking that the frequency of the event that goes above an AND gate is the multiplication of the different probabilities of this happening, right? Of all the events under the AND gate, while for the OR, you add the probabilities. So that's the basic, very basic gates that you use for fault trees. There are more, but that's more in depth. So to develop the fault tree, you normally start at the top, right? And you work backwards because you know what the end result is. You know what the end event is. It's an overpressure, for example. And then you say, well, for this overpressure to happen, maybe I need the causes and the safeguards to follow to fail at the same time, right? So normally in the process industry, you put an AND gate and you say all the causes here, all the failure of the safeguards there, and you multiply those two depending on how you're organizing your tree. But that's the way to go normally, where you always have a cause and the failure of the safeguards, and the product of those leads you to the top event, right? Leads you to a hazardous event. And you stop developing these when you get to basic events that can be quantified, like a failure of a valve, a failure of a pump, for which we have reliability figures that we can use. So always be aware of the units and the fact that some initiating events are probabilities and some are frequencies. And you shouldn't be multiplying two frequencies, right? So you cannot multiply things with units in this way. So you have to be careful how you combine the events so that it actually makes sense in real life, what you're trying to develop in the tree. And always check your units, because something that happens when you're doing this is that sometimes you get a frequency per million hours and a frequency per year. And if you're not careful and you combine those, it doesn't make sense anymore, right? So you always have to be careful with what's a probability, what's a frequency, and in which units the frequencies are. But that's how you basically build fault trees. I hope if you're here, you more or less know something about this. So now that we are reaching sort of midpoint, I wanted to go through an example, which is what I think it's interesting for these things, right? So imagine the scenario that I was talking about before. You have different pressure sources, right? So you may have 8 different sources. 4 of them go to one manifold, 4 of them go to another manifold. Each of those manifolds has a common isolation valve, and then you join those 2 manifolds and you have a further common isolation valve and then a separator. And imagine the system is only fully rated, so it's designed for the maximum pressure that this source can generate up to here, right? Up to the first isolation valve. So if you close this, you will overpressure these 4 lines, right? So to prevent rupture of these lines or overpressuring these lines, you have added PSVs and you have added safety instrumented functions, right? But you've done that in each of the lines, in each of the source. So if this common one closes, all of these safety instrumented functions need to work at the same time for the system to be properly protected. While if this one closes spuriously, for example, everything else, like all the 8 sieves, need to work at the same time. So if one of the sieves and one of the PSVs fail at the same time, when this event happens, you have overpressure of the system. So all of these needs to work at the same time. That's when LOPA becomes too unidimensional. So how do you determine the SIL that each of these safety instrumented functions need to have? You may do a preliminary LOPA to know the ballpark, where you take one line, right? And you do the LOPA for one of these functions following one line until the inlet separator, and that will give you a ballpark figure, but it's not the correct way to do it, because you need to consider the interactions between this function and all the other functions. So that's the challenge when you want to do this. So the first thing you have to do is to create a top event, right? And our top event is overpressure in any of the segments that are not fully rated in the system, right? Remember here that, your imagination is the limit to how you want to develop this and how you want to organize the tree. As long as it makes sense logically, you can do whatever you want, right? So this is what I've decided in this case. So Overpressure of any section that is not fully rated. Notice I've left the separator out because the separator would have its own PSVs and would have a high pressure trip that closes this, right? So the separator would be protected. That's what I've imagined. I know it's not written there or anything, but that's what I've imagined for this scenario. So note that we don't need to worry about the fully rated parts of the system either, because those are fully rated. So closing this is not an overpressure. That's it. Closing this it's a production loss, but it's not an overpressure, right? And as I said, we don't need to worry about the separator. So we need to worry about this, right? Now, I've divided that into 3 different segments, right? To make it easier for me to think of these in steps, right? So I've broken this down in segment 1, segment 2, segment 3. And of course, 1 and 2 are going to be more or less the same because we have sort of the same design. It will depend as well on what the pressure sources are for each one and whether they are similar or not. But this could be further divided. But this is the way I preferred to talk about it because I'm thinking of the initiating events, right? So if this closes, all of these need to work. If this closes, all of these 4 need to work. But if this closes, the 8 of them need to work. So I've separated that based on the initiating events and the safeguards that need to work for each segment of the production system. So then overpressuring any part that is not fully rated is overpressure in segment 1 plus overpressure in segment 2 plus overpressure in segment 3, right? So I put an OR gate and I say either this or that can lead me to an overpressure of any of the non-fully rated sections. That's fairly simple, right? So then we go to segment 1. Let's focus on the first segment. And that will occur if either XV1 or XV3 is spuriously closed, while the safeguards fail at the same time. So always, when you're building this, as I said, it's always sort of a failure of an initiating event happening, and then the safeguards that you have for that initiating event failing at the same time on the RAND gate, right? So if XV1 closes, then we have closure of XV1 and failure of its safeguards, right? So that's an initiating event, and that's a basic event because a spurious closure of an XV is something that you can find in reliability databases, or you can use a rule of thumb from industry. You can go to the CCPS LOPA book and take that, or you can take the spurious failure rate, the spurious trip rate of that safety instrumented function associated to that XV, or maybe you have data from your own organization on how many times per year an XV of a specific type closes spuriously. So, but we know there's a lot of data on isolation valves and when they close in error. So that we consider initiating a basic event, right? And then the failure of all the safeguards against this closing and creating an overpressure here, right? When you put a triangle, this means that this will go to another page because we don't have different enough space to develop that, right? And then we do the same thing for closure of XV3. So if XV3 closes, then it's a basic event and the failure of the safeguards. And note that I called this different to that because in S1, it's this. So it's the safety instrumented functions and the PSVs for sources 1 to 4, while for S2, it's going to be the safety instrumented functions 1 to 8 and PSVs 1 to 8 as well that need to fail. Any of them need to fail, and I get the overpressure event. So then, this is fairly simple. So now I'm going to develop the failure of the safeguards for segment 1, right? Now, if any of these safeguards fails, right? So first of all, you see I break it down into the different sources. So failure of safeguards for source 1, failure of safeguards for source 2, failure of safeguards for 3 and for 4. And the sum, if any of those fail, I get a failure of the safeguard. So they all need to work at the same time. Therefore, if this fails, or if this fails, or if this fails, or if this fails, or very importantly, something that you cannot consider in LOPA, if I have a common cause that makes all of the SIF fail, or I have a common cause that makes all of the PSV fail at the same time. So for example, it could be a systematic error where the maintenance personnel is doing incorrect maintenance of the PSVs, or if the fluid that's going through each of these PSVs is making, it's so foul that it's not allowing them to open, or if there's any design problems with them. So there could be common cause failures for the different technologies that you're using to protect your system, and you have to consider those when you're doing the fault tree, which you cannot do when you're doing LOPA. So then the failure of the safeguards of any of these sources will be combined under an AND gate as the failure of the SIF and the failure of the PSV, right? So if the SIF fails and the PSV fails, then the pressure from here will manifest, right? So that's an AND gate. And a failure of a safety instrumented function, I forgot the gates here. It's going to be the failure of the PT. This should be an OR gate here, or the failure of the logic solver, or the failure of the shutdown valve, right? So this is pressure transmitter, a logic solver, a shutdown valve. So if any of those elements fail, the safety instrumented function fails, right? If any of those fail, so an OR gate here, this fails, and if this fails and the PSV fails, then I have failed the safeguards for source one, and then I have a failure of all the safeguards, because if one of them fails, all of them fail. And then if I combine that with the closure of the XV, I get overpressure of segment one, which directly takes me to overpressure of the not fully rated section, right? Now, the tree is sort of built. To do overpressure of segment two is basically the same. To do S2 is basically this, but considering all of the 8 sources at the same time. When you have more sources, you will see that, or when you have more things under an OR gate and more common cause failures, you will see that the probabilities are starting to spike, right? And you cannot consider that in a LOPA. You cannot consider these interdependencies during a LOPA. So you can see how the fault tree starts to become bigger and bigger and bigger, right? The easy thing of this is that it's a lot of initiating events that you know the frequency for, and you know, for example, a failure of a PSV, how many times per demand that happens. So this is a frequency. This is probabilities of failure on demand, right? So these are probabilities, these are frequencies, and then you multiply them and you get frequency plus frequency, and then frequency plus frequency plus frequency, and then you have the frequency of the total event, and you know your acceptable risk target, right? So the only variable you have to play with is these 3 failures, right? So how many times per year, or sorry, per demand, does this safety instrumented function fail to achieve its intent? If I know this, then I can calculate that number. And then I can check that that number is in line with my acceptable target, acceptable risk target. So yeah, to continue developing the tree, as I said, you follow the same approach. But then how do you calculate the SIL of each safety instrumented function with this process? As I said, we know the frequency of the initiating event. We know the probability of failure on demand of the PSVs. We know the frequency target for the top event, and we can assign common cause failures based on the PFD of the SIFs. So this initiating event is related to all of these initiating events, right? So the only missing information is the probability of failure on demand of the safety instrumented function. So what you can do is perform the fault tree calculation. So see here, I have collapsed these 3 into one basic event, because really this is what you need to play with. And then after that, you can decide how to build your safety instrumented function. But what you want to play with is, what you need is the probability of failure on demand of each of these safety instrumented functions. So what you need to do is an iterative process where you change the probability of failure on demand of each of these SIFs until you get your acceptable risk target, right? And you can do that with fault tree analysis software that is fairly simple to do. So that is the way that you would find the required SIL for each of these functions at the same time. You cannot do this with LOPA because LOPA will only let you do one path. LOPA will not allow you doing the 4 paths and the common causes at the same time. I think maybe you could do it, but it's going to take you a lot longer to develop that worksheet than doing it with a fault tree. So this is much, for this type of scenario, for this type of event, this is much more simple. This is a much better approach. It's more detailed. It's going to give you a lot more information as well. It's going to tell you what the easiest path to failure is. So it's going to give you a minimal cut set that it's going to say, if this and this fail, you have overpressure. So be careful with those elements. Maybe you want to put more risk reduction in some of these places and not in others. This is a very simplified problem, right? So you wouldn't get that much information from something like this, but it will, when you encounter problems like this in real life, you do need, it is very useful to have the minimal cut sets that take you from initiating events to top event, because then you can see what part of your process is most vulnerable. So yeah, you iterate until you get that number. Then you have the target for this. Once you have the target for this, you can decide whether you need 1 transmitter or 2 transmitters and what voting you should use. And you can check what the probability of failure on demand of each of the components of the SIF is and what the architecture should be. Because remember, we're only doing this for SIL determination. We only want to know how good that safety instrumented function needs to be. And yeah, that is the way that you would use fault tree to calculate the required SIL for a lot of safety instrumented functions that are working in one system at the same time to prevent against a single hazardous event. Now, to cap it off, I want to go through that slide again, when to use the FTA for SIL determination. As I've said multiple times, most, like 95 to 98%, 99% of the scenarios out there are LOPA is absolutely fine for them, and it will give you the level of detail you need. And it's a good, it's a very good time or value tool to use, right? So you'll get all the value you need in a very much shorter time than if you did fault tree analysis for all the scenarios. So for most of them, you should do LOPA. However, when you have something like this, where you have multiple SIFs that need to work at the same time, and if any of them fails in a common initiating event, then you have a hazardous consequence somewhere in your system. Then you need a fault tree analysis, because a LOPA is not going to give you the level of detail required for this calculation and required to solve this problem. Okay. And also, yeah, when you want to look into common cause failures, if you want to be more conservative than you can be in a LOPA, and you can check, are we introducing common cause to any of these, or to any of these that can actually increase the probability of all of them failing? And then how is that impacting my overall risk reduction model? So that's when you use this technique, because you want to really make sure that the system is fully protected. Of course, this also happens when you have, or normally when this happens is you have very high pressure, high temperature systems with a complex sort of grid, a complex layout, and with terrible consequences, right, if something goes wrong. So you tend to use this for the very worst of the scenarios to really make sure that your system is sufficiently protected, because if it's not, the consequences may be catastrophic, right? So that's when you really want to go in depth, and you may want to do a fault tree analysis of your system to determine what the required SIL of each of your safety instrumented functions should be. And yeah, I think I hope that was quick enough but sufficient detail. I know I didn't put numbers on any of these, but I think numbers are not that important. It's more important to understand how the technique should be used and when the technique should be used. And basically, to me, the important part is that people understand you are the one defining these, because you are playing, you're doing an iterative game here of playing with the probability of failure of these to reach an acceptable target, because you know all the other variables in this equation. So yeah, I think understanding how to apply the technique to get what we want is more interesting than throwing numbers out. But yeah, that's it for now. I have a few questions, not many, but I have a question here from Saman. So I published that. So, for example, would you consider overpressure in each SIF, or, for example, only in SIF1? So overpressure is in any of these three segments, and it's protected by SIF1 to SIF8 at the same time. So that's why this is more complicated, right? Because as you rightly put it there, Saman, we are used to think about one SIF protecting one scenario. And that's the way we are trained to see this. And that's why, yeah, our first instinct is to go through LOPA, right? Or something like that, and say one SIF, one scenario. But all three analysis you do when you have a sort of different problem where you have several SIFs, one scenario. And then it would be, I would consider overpressure in, not for each SIF, but in the system. So overpressure in any part of this system, protected sometimes by 4 SIFs at the same time, sometimes by 8 SIFs at the same time, but in parallel. So if any of the SIFs fail, my system will go to overpressure, and that's the complexity of this. I hope that answers the question, Simon. Now Idris asks, instead of deriving from trial and error, is it possible to identify the exact PFD of each SIF? Yeah, I mean, I don't know how you would do that, because again, we're looking at all of them at the same time. So to me, the way I have achieved this is through iteration, right? Or alternatively, some companies or some operators already know what they have, right? The system is existing and they already know the SIF they have there achieves SIL 1, and yeah, they have a PFD of whatever X, and so you know you have X here, and what you calculate then is you just calculate whether you achieve tolerability, acceptable risk target or not. So, however, through trial and error, through an iterative process, you will find the exact PFD of each SIF. And in an example like this, what I would try to do, because if normally if it's wells, for example, you do have the same design for all of them, more or less. So you will have like a wing valve, a master valve, or a couple master valves, and then a wing valve, and then a choke valve, and then blah blah, and you have the same arrangement for most of the wells, right? So I would try to define the same number for all the SIFs, so I can design them all in the same way. But then you would be careful on how you do the proof testing of all these SIFs and whether you want to do it staggeredly or not, because maybe you want to stagger the proof test of each one of these to reduce the common cause failures that maintenance could be introducing here to reduce these to the common cause failure for the SIFs. But yeah, you can follow different approaches. If you already know what you want here, then you can check if you are achieving that. But if you don't know what you have here yet, then you can just define this and play with that. Now, Thank you. Let's see. Solak says, thanks for the presentation. Thank you for listening. As an advantage of fault tree analysis, I suggest also mentioning the determination of minimal cutsets and the qualitative analysis of the fault tree. Yeah, exactly. What Solak said, this allows for the identification of weak points in the system. That's absolutely true. Yeah, we mentioned that with fault tree analysis, it's a lot more powerful than only allowing you to calculate the frequency, because as Solak says there, you can then know what the most vulnerable part of your process is, because you can define, well, if this fails, only with the failure of this, and then that, I will get to the top event. So if you define the minimal cut sets for the fault tree, then you can get what is the easiest way from you to get from an initiating event to a top event. And maybe once you develop your fault tree for your system, you realize, wow, we have one basic event, which only has one protection layer between us and an overpressure event, for example. So then you can work on that scenario, because also when you calculate the fault tree, you will get the numbers for each of these gates, right? So you will get the calculation, the result for each of these gates, and then you can see which of these gates contribute more to the top event, and you want to focus on reducing the frequency of those gates then. So yeah, very, very interesting coming from Solak. Someone is asking, how do we determine the acceptable frequency of the top event? As I said, this may be set by the regulatory framework of the country you work in. So for example, in the UK, the Health and Safety Executive has published a guideline years ago, which has some guidance on what is risk tolerability, what the risk tolerability criteria should be, right? So if you're in the UK, you will follow the Health and Safety Executive's advice, because that's the law in the land, right? While in some other countries, there is not any guideline from any regulator. However, an operator may have its own numbers, right? So for example, I don't know, I don't want to say names of companies, but different operators in oil and gas, major operators in oil and gas, they do have their own numbers for what they consider acceptable for safety, for environment, and for money. How do you select these? How do you determine that as an organization? The safety one, my advice would normally go to the Health and Safety Executive of the UK, because it is a very comprehensive guideline, and it's sort of accepted in many places as and it is a reputable source, right? There are some explanations as well in some Norwegian Norshok documents, so you may want to go through those. Norshok has some guidelines on what frequency is acceptable for some overpressure events in some segments of offshore plants, for example, offshore platforms. And for money, for example, acceptability for money, it's up to the organization to decide. Regulators normally don't have a view on that, so that's up to the organization. And what normally most of these organizations do is you create sort of a risk matrix, and you calibrate, or you do a graph, and you calibrate it from, we say one fatality, for example, is 10 to the minus 5, which is more or less what the HSC says, right? So nowadays it's mostly considered 1 in 100,000 to 1 in 10,000 years is acceptable for a single fatality across different geographies. So you take that as a calibration point, and then you say, well, if I have 2 fatalities this much, if I have 6 fatalities that much, if I have 10 fatalities that much, and you start doing a line, right? And then you can say injuries is 10 to the minus 3, fatalities 10 to the minus 5 or 10 to the minus 4, and you sort of do a line with that. And then the environmental ones and the financial ones you may base on the safety ones. I hope that helped. Yeah, someone asks if is SIL verification necessary after SIL determination? Yeah, well, depends. If you find that these safety instrumented functions have a SIL requirement, right? You need a SIL one or SIL one or more to get to that acceptable risk level, then yes, you need to do SIL verification. So you need to calculate and demonstrate that each of these safety instrumented functions will achieve that in the design stage, will achieve that in real life, and then you need to test them every year to make sure that that's still the case. So basically, you need to follow the functional safety life cycle for each of these functions if you find that they do have a SIL requirement. Someone says, hmm. So Salman also asks how the overpressure in SIF 5 to 8 can have an effect on SIF 1. It seems like a redundancy system or operating safe loop function. No, the cause is, for example, if you close XV3, you need both, well, not both, you need SIF 1 and 5 and 8. You need all of them to work at the same time. So remember, we're not looking at the frequency of overpressure in the SIF. We are looking at the frequency of overpressure in the system. So this is what we are protecting. The equipment under control is the production system. And for example, when this closes, we need all of the safety instrumented functions to work at the same time. None of them can fail. So that has an interaction in all of them. Also, there may be systematic failures or systematic errors introduced in the system if you use the same type of valve for all the same SIFs, for all the 8 SIFs, or if you use the same type of transmitter, or if you are maintaining them in the same way, or if there is a manufacturer error with some of them, or you're calibrating them the same way, so there's a calibration error with all the pressure transmitters. So you may have common failures to all of them, and if one of them fails when this closes, you have overpressure. So that's gonna be, to calculate the probability of overpressure here, if you only had one pressure source, you would only use one SIF. But if you have 8 pressure sources, is the sum of the failure rate of all of them. So the probability of this failing plus this, plus this, plus this, plus this, plus this, plus this, plus that. So it becomes, so each of them have to become a lot better than if you only had one source of overpressure. They are not redundant. They are all working in parallel, not in series. So that's how the probability of this affects the probability of that, because they are added when you are looking at this closing. So you need to add the probability of failure of all of them. And the lower that becomes, the more likely you are to achieve the required risk reduction. But if you have 200 wells, good luck. You may have to find other solutions, or segregate the system in a different way. But yeah, this is just an example. Let's see, another one. When we are validating the loop during proof testing, should we do the test like in this tree, for example? Should we need to see that all the SIFs worked at the same time? No, you can perform proof testing for each SIF individually. You should perform it for each SIF individually, because what you want to do is, we have already determined the SIL requirement for each of these SIFs. Now, how you manage them in real life is a different thing. You can just go and test. I would even stagger the proof test to make sure that I'm decreasing the probabilities of common causes failing, right? So maybe you have different maintenance crews doing them every 6 months. You do, every 6 months you do 1, 3, 5, and 7, and then the next 6 months you do 2, 4, 6, and 8 by 2 different maintenance crews or something, to make sure that we are sort of doing them independently. So yeah, you don't need to do them all together because a demand will be a demand no matter where the demand happens in the system. So a demand in XV1 is the same as a demand in XV3 for the SIP. The SIP doesn't know what the cause is. So you're just checking that it still maintains its probability of failure on demand. So that's it. Let's see. So Italy is saying if we can share the presentation. I published that one now. Absolutely, we can. Yeah, someone has a good question here. Is it possible to use bow tie instead of fault tree analysis? And I would say yes. I mean, yes, because you could also use reliability block diagrams rather than fault tree analysis, because these are different ways, different representations of the same problem. The only thing with bow tie is that I wouldn't do it, because for bow tie you normally do bow tie to see preventative against mitigative functions, right? And how, or not functions, protection layers. So bow tie is more, what do I have in prevention? What do I have in mitigation? And checking that this is balanced, that I have a good balance of prevention to mitigation for one scenario. So you don't necessarily even need to do probabilities in fault tree, not necessarily. But yeah, you could sort of, if you flip this and you put it, if you flip the image and then you put the overpressure in the middle, then you would sort of have a fault tree on one side for prevention and an event tree on the other for mitigation in a bow tie. So yeah, you could use this. I mean, you can express these mathematically in different ways. You could also do reliability block diagrams of this, but fault tree to me is the way to go when we want to calculate probabilities of failure, especially because of what Solak said before. Because fault tree also gives us minimal cut sets, and it lets us know what the most vulnerable part of the process is. So that's also good for fault tree. So someone asked also why we didn't include the separator in this discussion. Yeah, it's just because I've imagined. So I made this up. So in this case, I've imagined that the separator has PSVs and a high pressure trip, which would close this XV. So the separator has its own protection layer, right? So when we do a fault tree, for example, if I close this, it wouldn't be overpressure in the separator. If I close this, it wouldn't be overpressure in the separator. It would be if I close its pressure control loop or the gas outlet from the separator, that would be high pressure in the separator, right? So, but that would be protected by other protection layers in the separator. Of course, you could sort of join everything. If you ever later want to do overpressure in any part of the plant, you could do like a huge fault tree for everything, but it's gonna take you a lot of time and it's not gonna add a lot of value. So yeah, that's why I didn't include it, because I've imagined that it has different protection layers. But yeah, that's most of the questions that we had, and we are a little bit over time, not much, just a little bit. So I think, what do you think, Nazar? We close this one out. I'd like to thank everybody very much for coming in and listening to this, and I hope it was useful. We always try to make this useful for you, so you can, apply these things. I like that we can share experiences and we can share different points of view in industry, so we all learn from each other. So it's been a pleasure just talking about this. So thank you so much for joining.